Here's my lab on the motion of a falling object. I would like to introduce the lab by talking about the two forces that play a role in determining the motion of a falling object, and these forces are gravity and drag force. We use the momentum principle to derive a position update formula in order to determine the change in the position of an object as these forces are acting on the object. The first force we'll take a look at is the force of gravity, also known as weight, and we can calculate this force by multiplying mass times the gravity constant 9.8 if the object is on Earth times j hat. One thing to note about the force of gravity is that while mass is used to calculate it, mass does not actually affect the changing velocity of an object, because as you can see here, the net force is divided by mass, so mass cancels out. Gravity is an attractive force in the direction of the object with greater mass, which in our case is the Earth. So based on what we know about gravity, we can see here that if the only force acting on these objects is gravity, they will both move towards the Earth at the same speed. Drag force considers the nature of the object, unlike the force of gravity, and it's a force that works in the opposite direction of the motion of the object. So we can use drag force to explain why a brick falls faster than a feather when dropped at the same height. When calculating the force of drag, we use the formula drag force is equal to some constant times the magnitude of the velocity squared times the unit vector, where c is dependent on the nature of the object, and we can use this formula because drag is a nonlinear force. So now we can recalculate net force to include both gravity force and drag force, and use this new value in our position update formula to predict the change in position of our object. In this representation, we can see how drag force and gravity force act in opposition to reduce the motion of the object. We are interested in knowing about these forces because we want to be able to predict the motion of an object as accurately as we can as it falls through space. And the only way to do this is by accounting for all of the forces acting on the object. We can see this on our graph, which shows our observed data in comparison to our predicted data with only the force of gravity and our predicted data with only the force of drag. As we can see by this orange line, there's a great amount of deviation between the observed data and the predicted data with only gravity force. We can see by the gray line how this deviation is significantly reduced once we account for drag force, producing a much more accurate model to predict change in position. The orange line reflects the motion of an object falling with no force acting in opposition, which is why the object is falling much faster. The gray line shows the object falling with drag force acting on the object, which reduces the motion of the object. This reflects the principle previously mentioned in the introduction. In Tracker, we are able to see as I drop my object from a fixed height. As you can see, the object deviates from the axis slightly towards the end. In order to improve my data, I would choose an object with a more uniform shape, such as a sphere, because as you can see from my video, the object I chose turns throughout, which could have changed the amount of drag force acting on the object at each given time. If we take a look at our code without drag, we can see how the only arrow present when we run the code is the one that denotes force by gravity. The graph is continuously nonlinear because there is no opposing force that allows the object to reach terminal velocity. In our second code, with drag, we can now see a blue arrow that grows with time, and this denotes drag force. The position versus time force becomes linear as the object reaches terminal velocity. For the what does it mean question, we can use the model with drag force to determine the terminal velocity, because terminal velocity can be defined as when the force of gravity and force of drag are equal, so we must look at the model that accounts for drag force. The terminal velocity is where the graph begins to flatten out as it reaches the asymptote. For the what if question, we can see from these two models, one that starts at rest and one that starts with an initial velocity, that the terminal velocity remains the same when an object is thrown downwards. We can see in both of these graphs that the object reached terminal velocity at about -1 meters per second. Thank you for watching.